Hello everybody. I want to move on today and look at what happens as a sample of a radioactive material is decaying. Now we were looking in the note for 19.3 about alpha, beta, and gamma decay, alpha, beta plus and beta minus decay, and gamma emissions. What's happening here? As the sample sits there, the element is transmutating. It's converting into another element, or maybe more than one element. And as that's happening, my original sample is disappearing. It's turning into something else. So what we want to look at today is, can we predict over a period of time how much of my sample will be remaining if I know what sample I've got? Now, in the textbook, talks about the concept of a half-life. Now, what I know is if I've got 100 atoms that are radioactive, that are unstable, sitting in a test tube, what can happen is at some point one of them may transmutate. It will turn into another element. So I'll now only have 99 of my original atoms left as that element. The other atom's still there, but it's something new. So I've got 99% left of what I started with. And then that one that changed had a probability that it would actually change into a new element, that it would actually decay. Every element, every of those 100 atoms in there, every one of them has the same probability that it will decay. But remember, probability is a random thing. Now, over a large number of events, we can predict with some kind of certainty how often something will happen, right? But ultimately, at the end of the day, the idea that atoms will decay is actually a spontaneous and random event. So, means it could happen, it might never happen, or maybe it'll happen in this second, or maybe it'll happen next year. So, for every single decay, it's really a random and unpredictable thing. But if I look at a large number of events, I can actually determine a statistical probability that something will happen. We kind of do the same thing in a lot of, let's say in cities, we can say if we know how many streets, or how many cars are on the street, and we know how busy the streets are, we can put an algorithm together, and we'll say we're going to predict that last year, the average number of collisions per day on this street is whatever the number is, 1.4 collisions every, say, per week. Now, that doesn't necessarily mean that we're going to have 1.4 in the same week next year, but if the average for the whole year was that, I can predict with some kind of certainty, because it's a large sample size, I might be able to look at, that's a small sample size, so it may not be that reproducible. But if I'm looking at a large sample size, if I'm looking at something that happens very, very often, and again, notice that what we have here are billions, trillions, quadrillions, whatever, trillions of events happening, so the probability becomes statistically predictable. Now, what that means is we can come up with a mathematical model to predict how much of a sample will be remaining after a period of time if we know how fast it decays. Now, what that number is that we're talking about is something called a half-life. Now, a half-life is the amount of time that it takes for exactly half of the sample that we started with to decay. Right? So if I look at carbon-15, which is going to beta-negative decay, which means I'm going to create a proton and kick out an electron from a neutron. This happens, half of it will have transpired, will have transmutated in 2.5 seconds. So if I give you a 100-gram sample and I wait for 2.5 seconds, after 2.5 seconds, half of it will have gone. Now you might think, okay, so if 50 grams goes in the first 2.5 seconds, 50 grams must go in the second 2.5 seconds. Well, no. What happens is of the sample that I've got at any point in time, I know that half of it will disappear in 2.5 seconds. So in the next 2.5 seconds, I'm going to go from 50 grams down to 25 grams. In the next 2.5 seconds, I will half that number. In the next 2.5 seconds, I will half that number. So recognize that ultimately, this will never completely run out. Now, it maybe get to a point where it's undetectable, right? Or if every single last one was to disappear. But because there are, like I said, huge numbers of these things, this can go on for a long time before we actually get to a very small number. Now, we've got a mathematical model that I said we're going to use to look at radioactive decay. And we use this for a lot of things in science, but we're going to talk specifically here about radioactive decay. And that's using the concept of the half-life. So the half-life is given the symbol of T1/2, right? And you can see it here in the formula, right, which is in the superscript. It's in the exponent, sorry. That 1/2 times to the power of the time that it's been going on divided by the time that is the half-life for that particular element. Now, if I look at any of a number of different elements, they all have their own half-lives. So oxygen 19, it has a half-life of 29 seconds. So again, if I was to give you a kilogram of oxygen 19, after 29 seconds you'd have half a kilogram. After 29 more seconds you'd have a quarter of a kilogram. After 29 more seconds you'd have an eighth of a kilogram. Right, so you get the idea. So that's the time it takes. So it wouldn't take long for this thing to become very small in amount. Some take fractions of a second. I'm looking here in the chart in the textbook. It says polonium-214 has a half-life of 1.6 times 10 to the negative 4 seconds. That's 1/10,000th of a second, and half of it's gone. Another 10,000th of a second, and half is gone again. Another 10,000th of a second. That's right. You get the idea that within a single second, there's going to be very little left, if maybe not even measurable amounts. And again, we'll talk about how we measure them. Well, we measure them using a Geiger counter, right? The Geiger counter is the device that measures the amount of radioactive decays of photons of energy that are given off by a sample, and we can measure the rate of decay using the Geiger counter. Right? It tells me how radioactive something is, or how many photons of radiation are given off. All right, so our formula here, I'm going to write it out. So A, the amount that I have at any point in time, is equal to the amount that I started with, right? AO is my starting, AO is my starting quantity. Right, AO is my starting quantity, and A is the amount that I have at time t. So if I start off with a certain quantity, A0, maybe it's a gram, right? And I look and I say after after so many seconds, how much will be left? After so many minutes, how much will be left? After so many years, how much will be left? And it depends on what the half-life is. If it's got a very long half-life, so something like cobalt-60, which is used quite often in science and medicine even, cobalt-60 has a half-life of 5.3 years. Right, so after 5.3 years, half it will be gone. Now, if I look at carbon-14, which we use for dating dinosaurs, and again, how do we know that that dinosaur was here 62 million years ago? Well, we use carbon dating. We look at carbon-14, and we look at how much carbon-14 is left compared to the other isotopes of carbon, and it gives us an indication of how much has decayed, and then we can work backwards to find T, the time that it took to get to that point, because carbon-14 has a half-life of about 5,000 years. So it takes a very long time for it to decay. Some of the isotopes of uranium, uranium-235, is 700 million years. Right, 7.0 times 10 to the 8th years. Uranium-238 has a half-life of 4.5 times 10 to the ninth years. Right? So what that's telling me is the rate of decay is very slow. Right? It's a very slow decay. Mind you, they give off very high energy emissions, so that's not to say that because they decay slow, they're not that unsafe. They are quite unsafe, right? Even with that slow rate of decay. So there's my formula, and I'm going to multiply that times 1/2, all to the power of the time that it's taken to get to this stage where we're trying to figure out the amount we have left, divided by the time it takes for half of it to disappear, or the half-life. Okay, so there's a formula that we're going to use. Okay, and all I'm going to do here today is I want to go through two examples. They're the two examples that are in the textbook here. So I'm going to jump, if I don't lose you, to my camera roll. And I'm going to look at, here's the first problem from the textbook. It tells us that the half-life for strontium-90 is 28 years. The symbol for year is annum. Again, think French, année. So 28 years is how long it takes for half of the sample to disappear. It says if we start with a 60-gram sample, if a 60-gram sample is currently in a sample of soil, how much will be in the soil 90 years from now? Okay, so if I know how long it takes for the half-life, which is 28 years, and I know how long we're talking, so let's just kind of work through this in stages here. So I'm going to switch to my whiteboard, even though the problem was solved for us there. Whoops. The problem was solved for us there. I want to solve it in stages. Okay, so we're told that the half-life is equal to 28 years. And we're told that we're looking for the amount that'll be present after 90 years. And we're told that our starting amount was 60.0 grams. Okay, so now I'm going to use my formula that says the amount let's switch pens here, is equal to my starting quantity times 1/2 all to the power of T, come on, divided by the half-life. Now, I wonder if I can make this bigger, if it'll write better. Okay, so I'm going to go ahead and solve now. So my amount that's going to be left in 90 years is equal to my starting quantity, 60 grams, times 1/2 to the power of 90 years, which is my T, divided by 28 years, which is my half-life. Now on my calculator, I'm going to start by taking this much here, and I'm going to do the math. So I'm going to do 1/2, which is 0.5, and I'm going to use my x to the power of y on my calculator to get an exponent. And I'm going to open the brackets on my calculator and divide 90 divided by 28 and close the brackets, and that gives me the answer for 90 over 28, which is 3.2. But remember, I've already done 0.5 to the power of this 3.2. If I hit equals now, I get 0.107, 0.108 is my number, times the 60 grams that I started with, times this now, and I will get my final answer, which says after 90 years, I will have 6.46 grams remaining. Okay, 6.46 grams. Okay, so it's a nice and easy formula. It's a little complex in terms of using your calculator, but it just takes a little bit of getting used to. Okay, I'm going to work the other way around. So this one says if I know how much I've got at the beginning and I know how long has elapsed, how much will be left, I can work backwards and say if I know what the half-life is, and I know how much I have remaining of my starting sample, I can figure out how long did it take for this to happen. I can solve for t here, which is a slightly different thing than what we've just done. Okay, so let's slide up here, and I'm going to do example 5. This one's going to take a little bit of practice. Okay, so we're told, let me see if I can just go back to the question here. I don't know if it's going to let me do this. Okay, so it says we've got the isotope, which is technetium-99, and it has a half-life of 6 hours. It says a new sample has 720 becquerels of radioactivity. Those are the units of radioactivity. On January 15th, it says how long would it take the sample to decay to 1/3 of this amount of radioactivity? Okay, so let's go back to our whiteboard here. So we're told that we have technetium-99 and that the half-life is 6 hours. 6 hours. I should probably make it a little more. Let's add another decimal place to this. We're told the amount of radioactivity that we have at the beginning is 720 becquerels. And it says the amount, sorry, that's my starting amount. The amount that I have after a while is 1/3 of that amount, which is 240 becquerels. Okay, so I now know my half-life, I know my starting and final amounts, and the question is, how long does it take to get that amount? So let's look at our formula now. A is equal to A naught times a half to the power of t divided by my half-life. Now let's put some numbers in here. My amount that I have is 240, 720, 1/2, t is unknown, and 6 hours is my half-life. Now, how am I going to solve for this? Because I've got the t up in an exponent. So I'm going to have to do something that maybe is new to you mathematically, I'm not sure, but I'm going to take the 720 from here and I'm going to move it to the denominator under the 240. So I'm going to get 240 over 720 is equal to 1/2 of to the power of t over 6. Right? And now what I need to do is I'm going to do something that you may or may not be familiar with. I'm going to take the logarithm of both sides. So on the left side, 240 over 720 is a third. So I've got 1/3 on the left. Okay, 240 over 720 is 1/3. So I'm going to take the logarithm of both sides. So if I take the logarithm of 1/3, or 240 over 720, it works just the same. It's going to be the same as a logarithm of 1/2 to the power of t over 6. But what we can do when we take a logarithm is I can take the exponent from up here and I can move it in front of the logarithm. So what I end up with is log of 1/3 is equal to t over 6 times the logarithm of 1/2. Right? Now let's just keep going here. I'm going to take my log of 1/3 on my calculator in a minute, divided by the log of a half. I'm going to take my log of 1/2 from here and move it to the denominator here under the log of a third, right? Divide both sides by log of 1/2. And what I've got now left on the left-hand side is equal to t over 6.0. And I'm going to take my 6.0 up to the front here. So I'll get t is equal to 6.0 times the log of 1/3 divided by the log of 1/2. Okay, and if you try that on your calculator, I would do log of 1/3, then divide it by log of 1/2, then multiply the whole thing times 6. So I would do this math here, and then multiply it by 6. So if I take the 1 divided by 3, and take the log of that number, it's negative 0.477, divided by, open my brackets, 1 divided by 2, or you can just do a half. Close the brackets, so I've got a half, and I need to take the log of that number, which is negative 0.3. If I hit equals, I now get log of a third divided by log of a half, which is 1.58, times 6, and I'm getting 9.51. Notice the units for time were hours, so the units for time will continue to be hours. Right? So this is telling me that in 9.5 hours, I will go from 720 becquerels of radioactivity, that's the quantity of radiation, down to 240 becquerels of radioactivity. Right? Now you think, well, if I'm going down to a third, shouldn't it be... Oh no, I guess I'm not even going to try to pretend to do the math here. I'm just going to use the formula, and I'm going to solve for the amount that should be left when all is said and done. Okay, so I'm going to finish there, actually. Nice short note for today. I haven't taken up any of the homework from last night, but I will go ahead and take up some of that homework. I'm going to leave you with the questions here on page 644. Right, there's questions A, B, C, and D. You'll see them about halfway down the page. And then there's 4 more questions at the end of the chapter that you can work on also. Now, once you're done this is a nice short day for us. You know, it always comes with at a price. I'm actually going to ask you to do maybe our last gizmo. I think there might be one more, I'm not sure. But this might be our last gizmo, and that's the gizmo called half-life. Right, so... Okay, so again, I haven't put them up there yet, but by the time I post this video, I will have posted the worksheets in PDF and doc file for you to work on and to run through the half-life. As you're doing it, be looking at the type of decay, the alpha decay, the beta positive positron decay, or the beta negative electron decay. And I think, again, as with the last gizmos, I think it does a really good job of kind of walking you through how this is going to work. Now, with some of the other gizmos we've done, they're labs that we could have and probably would have done some of them in class. This one we're not likely to be doing in class because we're not allowed to have radioactive isotopes in schools. If you were taking this physics class in the mid-1960s, maybe even into the early 1970s, you would have had a Geiger counter in your hand and you would have had radioactive samples in your hand. When I cleared out Scott Park a number of years ago, I was working at Scott Park when they closed, and we found all the radioactive samples and the Geiger counters that had been used earlier, before my time, as a high school teacher anyway. I might even have used them as a student. I can't even remember when I took physics in high school. But anyway, so I'm going to leave you with that. So the gizmo, so tomorrow, when you get this, it'll be Friday. So the gizmo will be loaded. I'm going to ask you to try and get the gizmo done over the weekend. You don't have a lot of the homework to do for this section. And then we're going to come back on Monday and we're going to do nuclear fusion and E equals mc squared. Right, and then we're going to finish up our last topic in this entire unit, which is nuclear medicine. And we'll be working on that going into next week. And then by Thursday, I believe it is, I have to check the calendar, I think it's Thursday, we'll have a test on both thermal energy unit and the nuclear energy unit, and I'll give you a really good review beforehand so that you'll be really prepared to do this. Okay, so again, not a lot of crazy math in this unit, more conceptual, trying to understand this alpha and beta decay and gamma particles, gamma emissions. Okay, so that's it for me. I will leave you for this, and I will come back next week, and we will pick up 19.5. Have a good weekend. Make sure to stay on top of hopefully you got your calorimetry